Welcome to the Explainer. Have you ever wondered how your password actually stays safe, even if a website's database gets leaked? Well, the answer comes down to two really clever cryptographic tools, hashing and MAX. Today, we're going to break down these silent guardians of our digital world. All right, so let's just dive right in with this question. When you create an account somewhere, they don't just, save your password in a big list. I mean, can you imagine? If they did, one single data breach would be a total catastrophe, exposing everyone's passwords. So instead, they use a really smart cryptographic trick. And the first part of that trick is something called a cryptographic hash function. Now, the absolute best way to think about this is like a unique digital fingerprint for any piece of data you can imagine. What's really amazing about this is that it's a one-way street. Think of a hash function like a super heavy-duty paper shredder. It's super easy to drop your data in and get a totally scrambled output. That's the hash. But it is basically impossible to take that shredded hash and tape it back together to figure out what the original data was. This image here just visualizes it perfectly. You can feed it any message. Doesn't matter how long. It could be one word or an entire book. And the hash function, our grinder right here, it just crunches it all down into a short, fixed-length string of characters. That final output, that's your hash value. So what is it that makes these digital fingerprints so incredibly powerful? Well, let's break down the key properties that are just absolutely essential for modern security. So we've already mentioned the first two, right? It's a one-way street, and the output is always the same size. It's also deterministic, which is just a fancy way of saying that the same input will always produce the exact same output. But this last one, the avalanche effect, this is where the real security magic happens. This property is so important. Why? Because it means that even the tiniest, most insignificant change you make to the input data results in a massive, completely unpredictable change in the output hash. This is what makes any kind of tampering immediately obvious. Okay, now look at this. We took the input hello world and we ran it through a common hash algorithm called SHA-256. Then we changed just one single character. The O became an X. The result? The new hash isn't just a little bit different, it's a totally new, completely unrecognizable string. That right there is the avalanche effect. So to bring it all back to our first question, this is how it works. The website never, ever stores your actual password. All it stores is the hash. Then when you go to log in, it hashes whatever you type in the box and just checks if that new hash matches the one it has on file. If they match, boom, you're in. The system knows you typed the right password without ever needing to save it. So hashing is a fantastic tool for making sure data hasn't been changed, right? We call that integrity. But what happens when you're sending that data across the internet? Well, it turns out that integrity by itself has a pretty big weakness. And here's the crucial point. Proving that data hasn't been accidentally messed up is a completely different thing from proving it hasn't been maliciously altered. Just checking the integrity of a message doesn't prove who it came from. It doesn't prove its authenticity. This diagram shows us exactly why this is a problem. Imagine Alice sends a message and its hash to Bob. An attacker, we'll call him Darth, can just grab it out of the air. Darth can change the message to whatever he wants. And then here's the key. Since the hash algorithm itself isn't a secret, he can just calculate a brand new, perfectly valid hash for his fake message. So when Bob gets this malicious package, he's going to run his own hash check. And of course, the hash is going to match the message he received. He has absolutely no way of knowing it's not the original message from Alice. See, hashing alone can prove integrity, but it can't prove who the sender really is. To solve this huge problem, we need to add a secret ingredient, something that only the sender and the receiver know about. We need a shared secret key. And that brings us to the Message Authentication Code, or MAC. The best way to think of this is like a digital version of an old-timey wax seal on a letter. It's made by combining the message with a secret key before doing the hashing. You simply can't create or verify that seal unless you know the secret. The whole process is actually pretty straightforward, but it's incredibly powerful. The sender creates a MAC tag using the message and their secret key. The receiver does the exact same calculation on their end with their copy of the key. If the two tags match, then Bob knows two things for sure. The message wasn't changed, that's integrity, and it had to have come from Alice because she's the only other person with the secret key, and that's authenticity. Okay, so let's put these two essential security tools side by side, because the choice between them really comes down to what specific problem you're trying to solve. This table really just lays it all out, doesn't it? A hash takes one input, the message. A MAC takes two, the message and that all-important secret key. And that single change elevates the security goal from just integrity to both integrity and authentication. That's why hashes are great for password storage, but NACs are absolutely vital for things like financial transactions or security APIs, where you have to know who you're talking to. So, what's the really crucial point to remember from all of this? Whether you're studying for an exam or just trying to get a better handle on how the web works, it all really boils down to a few key ideas. Here it is in a nutshell. You use a hash when you just want to check that a file hasn't been accidentally corrupted. But you use a MAC when you need to trust that a message sent over a network is both unaltered and from the person you think it's from. That secret key is the only thing that defends against a malicious attacker. And by the way, a really common type you'll see is called HMAC, which just stands for a hash-based message authentication code. So ultimately, picking between them comes down to your threat model. Are you trying to protect against accidental data corruption, or are you defending against a deliberate, sophisticated attack? Answering that one question is the very first step in building a secure system. So next time you log into your bank account or buy something online, you'll know a little more about the invisible cryptographic dance that's keeping your digital world safe.